We'll close this class by talking through a handful of advanced topics related to the course material. In this course, we've already discussed a variety of goals, methods, and paradigms of knowledge-based AI. Now let's close by talking through some of the advanced applications of this content. We'll also talk quite a bit about some of the connections with both AI and human cognition. Many of the topics we'll discuss today are very broad and discussion-oriented. So we encourage you to carry on the conversation on the forums and discuss some of the issues that this content raises. Visual-spatial reasoning is reasoning with visual-spatial knowledge. This has two parts to it, visual and spatial. Visual deals with the what part, spatial deals with the where part. So imagine a picture in which there is a sun on the top right of the picture. There are two parts to it, sun, the what, the object, and where, the top right of the picture. We have come across visual-spatial reasoning a little bit when we use constraint propagation to do line labeling in 2D images. One way of defining visual-spatial knowledge is to say that in visual-spatial knowledge, causality is at most implicit. Imagine a picture in which there is a cup with a pool of water around it. You don't know where the pool of water came from, but you and I can quickly infer that the cup must have contained the water, and the water must have spilled out as the cup fell. So in visual-spatial knowledge, causality is implicit, but it enables inferences about causality.
There are several ways of how we can deal with visual-spatial knowledge. In fact, in your projects, you've already come across some of them. So imagine there is a figure here. Here is a triangle with the apex facing to the right. Here is another triangle with the apex facing to the left. So in one view, the AI agent can extract propositional representations out of figures like this. And similarly, propositional representations out of figure like this. So this is a propositional representation, this is a propositional representation. And then the AI agent can work on these propositional representations to produce new propositional representations. So some AI agent can use a logic engine or a production rule to say that this particular triangle, which was rotated 90 degrees, has now been rotated to 270 degrees. So although the input was in the form of these figures, the action here was at the level of propositional representations of these figures. The AI agent may extract propositional representations like this through image processing, through image segmentation, perhaps using some techniques like constraint propagation as well. Alternatively, the AI agent may have analogical representations. In these analogical representations, there is a structural correspondence between the representation and the external figure. So the external world had a triangle like this, and the analogical representation will also have a triangle like this. Notice that I'm using the term analogical representation, which is a separate thing from analogical reasoning. We are not talking about analogical reasoning right now. We're talking about analogical representation. And analogical representation is one which has some structural correspondence with the external world that is being represented. Given such an analogical representation, then I might run affine transformations or set transformations to get this. So I may say that I got this triangle out of that one simply by the operation of reflection or rotation. So these propositional representations in the previous view are amodal. They are separated from, divorced from the perceptual modality. These analogical representations, on the other hand, are modal representations. They are very close to the perceptual modality. In human cognition, mental imagery appears to use analogical representations. What would be an equivalent theory of computational imagery? Human cognition is very good at using both propositional representations and analogical representations. Computers, however, are not yet good at using analogical representations. Most computers, most of the time, use only propositional representations. The same kind of analysis may apply to other perceptual modalities, not just to visual images. So here are two measures, and we can either extract propositional representations out of them and then analyze those propositional representations, or we could think directly about the relationship between these two particular measures. Here is a question for building theories of human cognition. When you're driving a car and you listen to a melody on your radio, and you're reminded of something, reminded of a similar melody that you had heard earlier, what exactly is happening? Are you extracting a propositional representation out of the melody that you just heard? And then the propositional representation reminds you of the propositional representation for a previously heard melody? Or does the new melody somehow directly remind you of a previously heard melody without any intermediate propositional representation? These are all open issues in cognitive science as well as in knowledge-based AI. In cognitive science, there is by now significant agreement that human cognition does use mental imagery, at least with visual images, but we don't know how to do mental imagery in computers. This chart summarizes some of the discussion so far. Content deals with the content of knowledge, and coding deals with the representation of knowledge, content and form. The content of knowledge could be visual-spatial, that deals with what and where. Where is spatial, what is visual. And the encoding for visual-spatial knowledge could be either analogical or propositional. An analogical encoding of visual-spatial knowledge, there is a structural correspondence between the encoding and the external world that is being represented. In the propositional representation of visual-spatial knowledge, there is no such correspondence. Examples of this verbal knowledge include things like scripts for going to a restaurant. The script for going to a restaurant, again, can be represented either propositionally or potentially analogically. In a propositional representation of the kind we saw, we may have tracks and props and actors. An analogical representation of the script for going to a restaurant, we may have a short movie. In much of the course, we have dealt with the right-hand side of this chart, with verbal knowledge and propositional representations. Part of the point of this lesson on visual-spatial knowledge and reasoning is that reasoning and knowledge can be visual-spatial and the representations can be analogical. But we have yet to fully understand their role in human cognition, and we certainly are yet to build AI agents that can deal with visual-spatial knowledge and analogical representations. One AI system that does do visual-spatial reasoning is called Galatea. It was developed by Jim Davies, here at Georgia Tech, about 10 years back, which is why it looks black and white and has this particular form. We provide a reference to the paper in the notes. There is a very famous problem in analogical reasoning called the Duncker radiation problem. The Duncker radiation problem goes something like this. First, I'll tell you a story, and then I'll give you a problem, and you have to try to find an answer to the problem. Let me begin with the story. Once there was a king, and not a especially good king, who ruled a kingdom. There was a rebel army that was trying to overthrow the king, but the king lived in a fortress, and it was very hard to overthrow him. Moreover, the king had mined the roads so that when the army went over the roads, that mine would blow off and most of the soldiers in the army would die. The leader of the army decomposed the army into smaller groups, and these smaller groups then came to the fortress from different directions. Because each group was small enough, the mines did not blow off, and each group was able to reach the fortress at the same time. There then, they were able to overthrow the bad king. So this was the story. Now let me tell you about the problem. There is a patient with a cancer tumor in his body. There is a physician with a laser gun. She can use the laser gun on this tumor to kill this tumor and cure the patient. However, the laser light is so strong that it will also kill all the healthy tissue in the way and the patient may die. What should the physician do? In most computer models of this problem is solved using propositional representations. So an example of a propositional representation for the original story might be that if there is a goal and there is a resource, and there is an obstacle between the resource and the goal, then split the resource into many different smaller resources and bring them to the goal all at the same time but from different directions. Most computational models of the Duncker radiation problem extract some causal pattern. The causal pattern might be that if there is a goal and there is a resource available, and the resource can achieve the goal, but there is an obstacle in the way, then decompose the resource into many smaller resources and bring them to the goal in the same time from different directions. The important part here is that this is the causal pattern extracted out of the first story. Once this causal pattern has been abstracted, it can be applied to this new problem. So the physician may decompose the laser beam into lots of smaller beams and put all of them to the tumor at the same time, thus curing the tumor. Jim wanted to ask whether one could do the same kind of problem solving without extracting these causal patterns. Could one use simply visual-spatial knowledge? So this is visual-spatial knowledge because there is both a sense of what, the fortress, as well as where in the middle of the figure. Notice this visual-spatial knowledge is represented propositionally. There are words like here like fortress and right road and top road and so on. But there is no causality that is explicit. You and I can infer the causality, but it's not explicit. His Galatea program was able to find a solution to the new problem by transferring this visual spatial knowledge to the new problem one step at a time. Thus, it would map this top body part to the top road one here, the left body part to the left road here, and therefore decide that this can be decomposed, this resource, denoted by this arrow, can be decomposed into smaller resources. And then the smaller resources can arrive at the central tumor from different directions at the same time. In this way, Galatea was able to solve the Dunker radiation problem without abstracting any causal pattern from it. Of course, one might say that the causal pattern is implicit here, and that is indeed true. But the entire point about visual spatial knowledge here is that the causal pattern is not being abstracted, but as long as it is a problem-solving procedure where each step is being represented only visual spatially, it is possible to transfer the problem-solving procedure to the new problem. We just saw an example where visual spatial knowledge by itself suffices to do analogical reasoning under certain conditions. Now let us look at a different problem. There certainly are situations where we might want AI agents to be able to extract propositional representations. Your projects 1, 2, and 3 did exactly that. One task where an AI agent might want to build propositional representations out of visual spatial knowledge is when an AI agent is given a design drawing. So here is a vector graphics drawing of a simple engineering system. Perhaps some of you can recognize what is happening here. This is the cylinder and this is the piston. This is the rod of the piston moves left and right. The other end of the rod is connected to a crankshaft. As this piston moves left and right, this particular crankshaft starts moving anti-clockwise. This device translates linear motion into rotational motion. I just gave you a causal account. Although causality was only implicit in this visual spatial knowledge, you and I were able to extract a causal account out of this. How did we do it? How can we help AI agents do it? At present, if you were to make a CAD drawing using any CAD tool that you want, the machine does not understand the drawing. But can machines of tomorrow understand drawings by automatically building these causal models out of them? Put another way, there is a story that is being captured in this particular diagram. Can a machine automatically extract that story from this diagram? In 2007, Patrick Yanner built an AI program called Architas. Architas was able to extract causal models out of vector graphics drawings of the kind that I just showed you. This figure is coming from a paper on Architas and hence the form of the figure. We'll have a pointer to the paper in the notes. This is how Architas worked. It began with a library of source drawings. These were drawings that it already knew about. For each drawing that it already knew about, it already had done the segmentation. These basic shapes, for example, might be things like circles, and the composite shapes, which were then labeled like piston and cylinder. Then a behavioral model or a causal model, which said what happens when the piston moves in and out, namely the crankshaft turns. And then a functional specification which said that this particular system converts linear motion into rotational motion. So there was a lot of knowledge associated with each previous drawing that Architas already had seen. All of this knowledge was put into a library. When a new drawing was input into Architas, then it generated line segments and arcs and intersections from it. And then it started mapping them to the lines and segments and arcs of previously known drawings. Retrieved the drawing that was the closest matching drawing to the new drawing, and then started transferring basic shapes and then composite shapes, and it transferred each element through this abstraction hierarchy all the way up to the functional level. As an example, if Architas library contained piston and crankshaft drawings like this, along with causal functional models for them, then, given a new drawing of a piston and crankshaft device, Architas would then be able to assemble a causal functional model for the new drawing. Thus, Architas extracted causal information from visual spatial representations through analogical reasoning. It may interest you to note that the projects you have been doing in this class are based on cutting-edge research. Until just a few years back, all computational models of solving problems from the Raven's test first extracted propositional representations from the figures and then ran propositional engines on those propositional representations. Thus, they may extract the transformation from A to B in the form of a semantic network shown here. And similarly, they may extract the transformation from C to 5 through the semantic network shown here. They would then compare these two semantic networks and decide whether or not A's to B is similar to C's to 5. You may have done something similar in your early projects. But in 2012, Metli Kunda here at Georgia Tech was able to write a computer program that used only analogical representations without extracting any propositional representations, and yet were able to solve problems on the Raven's progressive matrices test. It used only affine and set transformations over the analogical representations. So as an example, it would compare A and B by saying that there is a set transformation, this particular dot is no longer there. And there is an affine transformation, in fact two affine transformations, first that make this square bigger, and second that translates the position of the square from inside the circle to outside the circle. It would find similar affine and set transformations that would relate C and 5. That will compare the affine and set transformations, again without extracting any propositional representations. Little surprisingly, Metli Kunda's program called ASTI, for ASTI, was able to do quite well in the Raven's test. It solved 50 out of the 60 problems correctly. Then in 2013, Keith McGregor, again here at Georgia Tech, wrote another computer program that used a different kind of analogical representation called the fractal representation. And he was able to show that the fractal representation also enables addressing problems on the Raven's test with a good degree of accuracy. We provide references both Metli's work and Keith's work in the notes.
In this class, we have talked a lot about how AI agents must be able to reason about the external world. But the external world consists of systems of many different kinds. A system is composed of heterogeneous, interacting components. The interaction between components lead to processes of different kinds. These processes can occur at many different levels of abstraction. Some of the processes might be invisible. Consider an ecosystem. In an ecosystem, processes occur at many levels of abstraction: physical, biological, chemical. Some of these processes are invisible to the naked eye, but they influence each other. Similarly, in business, businesses are composed of a large number of interacting units: manufacturing, marketing, delivery, and so on. Each of these units can be described at many levels of abstraction, from individuals to teams to full organizations. Given that the external world consists of systems of different kinds, AI agents must be capable of systems thinking. They must be capable of thinking about the invisible processes of systems, about the complex behaviors of systems. In particular, they must be able to derive the invisible processes from the visible structure. This is systems thinking.
We can connect systems thinking to several topics we have already covered in this class. You may recall that early on in this course, we used frames to understand stories of this kind. Now, this story is actually capturing some information about a system. In this particular system, there is a country with people and president. It also has geological faults, as a result of which earthquakes occur that kill some people. So the components, the complex relationships between these components, and the complex processes that emerge out of those interactions between the components. Scripts, too, are related to systems thinking. Dining at a restaurant is a complex system. Once again, there are a number of components, relationships, interactions, processes, functions. A script is a knowledge representation that allows us to capture knowledge of a stereotypical dining experience at a restaurant. When we discussed diagnosis, at that time we talked about systems thinking a little bit more explicitly. To begin with, we said that diagnosis is identification of a fault responsible for a malfunctioning system. Diagnosis begins with the observed data about some system, validates our expectations of the behavior expected of it. The diagnostic task takes the data and maps it into a hypothesis about faults responsible for that behavior. What makes the diagnostic task so hard, again, is that there are a large number of components that interact with each other, and there's a complex behavior that emerges out of the interaction between those components. Just think of program debugging. Program debugging is hard because there are a large number of lines in the code, and these lines in the code interact with each other, and very complex behaviors, output behaviors, emerge because of those interactions.
So another good example of how diagnosis is a case of systems thinking is if we look at ecological systems. Recently, there's been a massive drop in the population of bees around the world. That's our data. Now, as it turns out, the cause for this drop in bee population is the presence of a poisonous substance in insecticides used in the past several years. However, we can't see the process of bees getting poisoned by this chemical. All we can do is infer it based on higher level interactions of seeing the bee populations drop and seeing a rise in this chemical. So in this way, there's multiple levels of abstraction in this process. There's the visible bee population, there's the visible use of pesticide, but there's also an invisible layer where the pesticide actually poisons the bees. So we have to discern the interaction between these multiple levels.
In any complex system, there will be many levels of abstraction, some invisible, some visible. The human eye or human sensors more generally can see only some of these levels of abstraction, the visible levels of abstraction. Systems thinking helps us understand the invisible levels. So AI has developed representations that help capture both the visible levels of abstraction, structure for example, and the invisible levels like behavior and function. Therefore, these models are sometimes called structure, behavior, function. Let's take a simple example. All of us are familiar with the household flashlight. You press on the button and light comes out of the bulb. What you can see is the button and the bulb and the body of the flashlight. You can even open the body of the flashlight and you might see some batteries inside the flashlight. That's all you can see. But of course, there is more going on here. To begin with, this particular flashlight has a function. This function is invisible. You can ascribe to it, but it's nowhere inside the body of the bulb. One level at which it is useful to analyze the flashlight is to ask ourselves, what does it do? Not yet, how does it work? Just what does it do? Its function. Here is a representation of the function. Here is the function create light of that light bulb circuit or the flashlight light bulb circuit. There is some stimulus, some external force on the switch. Initially there was no light, 0 lumens, and finally there is some light, 30 lumens. This captures the notion that when I press on the switch, light comes out. Here is a representation of the structure of the flashlight. Here is the light bulb, the switch, and the battery. And they're connected. All of them are attached. Here is the invisible causal process that we are calling behavior. We'll capture this behavior through a series of states and transitions between these states. So here is electricity, initially in the battery. Then this electricity flows from the battery to the bulb. And then the bulb converts this electricity into light. But in order for this electricity to flow through the bulb, this particular switch has to be in the mode on. The switch goes into the mode on when someone presses on it. Electricity is converted into light because that's the function of the bulb. Notice that these SBF models are nested. We just gave an SBF model of the flashlight circuit. But now if you want, we can get to the SBF model of the light bulb itself. How does it create light? In this way, structure, behavior, function models capture not just the visible structure, but also the invisible causal processes, the behaviors, and the functions. Moreover, they capture that at multiple levels of abstraction, at the level of the flashlight, at the level of the bulb, and so on. We will not describe it in detail here, but structure, behavior, function models and other similar models enable systems thinking in the context of diagnosis and design of complex systems. We provided some readings about this in the course materials if you want to read more about it.
When we talked about configuration, we alluded to design. Design is a very wide-ranging, open-ended activity. But then we settled on to configuration, very routine kind of design, where all the parts of the design are already known. We simply have to figure out the configuration of the parts. It is time now to return to design thinking. What is design thinking? Design thinking is thinking about ill-defined, under-constrained, open-ended problems. Let's design a house that is sustainable is an example of design thinking. Sustainability here is ill-defined. The problem is open-ended. In design thinking, it is not just that the solution that evolves, it is that the problem evolves as well. We have problem-solution co-evolution.
As we have mentioned earlier, configuration is a kind of design, a kind of routine design. And one method for doing configuration is plan refinement. In configuration, all the components of the design are already known, but we have to find some arrangement for the components, and we assign values to some of the variables of those components to arrive at an arrangement. Here is a design specification that one begins with. Here it might be a plan for designing a chair as a whole. And once we assign values to some of the variables at the level of the chair, then we can refine the plan for the chair into a plan for the chair legs, the chair seat, and so on. All of this might be subject to certain constraints. There are in fact a number of AI systems that do configuration design. Many of them are being used in industry. Some of these AI systems use methods like planned refinement, the way we have shown it here. Others use case-based reasoning. In fact, AI systems use a variety of methods for doing configuration design, including model-based reasoning and rule-based reasoning. What about more creative kinds of design? Design in which not all the parts are known in advance. Since we just discussed the flashlight example in the context of systems thinking, let us revisit that example in the context of creative design. So this is a schematic of the flashlight circuit. Here is a switch, the battery, the bulb, as earlier. Under systems thinking, we discussed how structure behavior function models capture the knowledge that when the switch is closed, electricity flows from the battery to the bulb, and the bulb converts that electrical energy into light energy. Let us suppose that this particular electrical circuit used a 1.5 volt battery and created 10 lumens of light. Tomorrow someone comes to you and says, I want 20 lumens of light, design a flashlight electrical circuit for me. How will you do that? You might go through the structure behavior function model of this particular circuit and do systems thinking. You may recognize that the amount of light created in the bulb is directly proportional to the voltage of the battery. So instead of creating 10 lumens of light, you need 20 lumens of light. You might say, I'm going to use a 3 volt battery. So far, so good. You've done systems thinking in the context of design thinking. But now let us add a wrinkle. Suppose that a 3.0 volt battery is not available. At this point, a teacher tells you it's okay if a 3.0 volt battery is not available. You can connect two 1.0 volt batteries in series. Two 1.5 volt batteries connected in series will give you the voltage of 3 volts. Accepting the teacher's advice, you can now create an electrical circuit that will use two 1.4 volt batteries in series and create light of 20 lumens. But you not just created this particular design, you also learn something from it. Every time you create a design, every experience is an opportunity for learning. In the mid-1990s, Sam Bhatta here at Georgia Tech created a program called Ideal. Ideal did creative design. In particular, Ideal would learn about design patterns from simple design cases, the kind we just talked about. I'm sure most of you are familiar with the notion of design pattern. Design patterns are a major construct in software engineering. But design patterns occur not just in software engineering, but in all kinds of design, for example, architecture and engineering and so on. Here is Sam's way of capturing the design pattern that can be learned from the previous case. If you know the design of a device that changes the value of some variable from one value to another value, and you want another design that changes the value of the same variable to some other value, not the same as the previous design, one way in which you can create the new design is by replicating the behavior of the previous design. So not just having behavior B1 for the first design, but having this behavior B1 as many times as needed. Let us connect this to the example we just saw. If you have a design of an electrical circuit that can create 10 lumens of light, and you know how to do it through some behavior B1, I need to design an electrical circuit that can create 20 lumens of light, but you don't know the behavior B2. Then, this behavior B2 is a replication of the behavior B1 by connecting components in series. Once Sam's program Ideal had learned about this design pattern of cascading, of replication, then, when it was given the problem of designing a water pump of higher capacity than the one available, it could create a new water pump by connecting several water pumps in series. Thus, Ideal created new designs in one domain, the domain of water pump, through analogical transfer of design patterns learned in another domain, the domain of electrical circuits. Viewed from the perspective of the new domain of water pumps, initially did not know about all the components, about all the water pumps that will be needed. But Sam's program Ideal was creative enough to know that the pattern of problems here in water pump is exactly the same pattern that was also occurring in the domain of electrical circuits. Sam's theory provides a computational account of not only how design patterns can be used, but also about how these design patterns can be learned and transferred to new domains. There is, of course, a lot more to design. We said earlier that design thinking engages problem-solution coevolution. It's not just that the solution evolves while the problem remains fixed, but that the problem evolves even as the solution evolves. It's not yet clear how humans do this kind of creative design where there is problem-solution coevolution. There certainly are few AI systems capable of problem-solution coevolution at present.
This brings us to the topic of creativity. We humans are naturally very creative. And I'm not talking just about an Einstein or a Mozart. You and I are very creative on an everyday basis. You and I constantly deal with novel problems. And when we deal with novel problems, we don't just give up. We address them, and most of the time fairly successfully. Now, the goal of knowledge-based AI is to create AI agents that can think and act like humans. So shouldn't we also create knowledge-based AI agents that are creative? But in order to answer this, we have to define what is creativity. Now, in lesson 1, we saw how hard it was to define intelligence. Defining creativity is no less hard, but we'll give it a try anyway.
In order to build AI agents that are creative, it might be useful to think about what is creativity. Please write down your answer in this box and also post your answer in the class forum. What do you think is creativity, David?
So after much deliberation, I decided that I would define creativity simply as anything that produces a non-obvious, desirable product. I think that we have to have some kind of output for creativity in order for it to actually be identifiable as creativity. I think that the output has to actually be wanted in some way. Doing something that no one wants is not necessarily creative. I think the output has to actually be desirable in some way, and it also has to be something non-obvious. Doing the obvious answer is not a very creative solution. If I'm propping open a door and I use a chair, that's a slightly more creative solution to that problem.
Thank you, David. Of course, everyone's answer to this question might differ. For example, some people may not put the word product here. It's not clear that the result of creativity is necessarily a product. Some people may not put the word desirable there because sometimes creativity may not result from some initial desire. Let us carry on this discussion of what is creativity on the forum. Feel free to add your own notions. In the computational creativity community, whose goal is to develop AI agents that are creative in their own right, the current definition of creativity is that something is creative if it is novel, valuable, and unexpected. Notice that this deals not just with creativity in the sense of design creativity, but with all kinds of creativity. So this could be a scientific discovery that is creative, novel, valuable, unexpected. This can also capture art or music. The notion of value there may not be a monetary value, it might be of some interest to a recipient. Creativity typically involves both a producer and a receiver. Notice that this notion of unexpectedness is connected to David's notion of non-obviousness.
So Ashok, what exactly is the difference between novelty and unexpectedness? If something's novel, isn't it also unexpected?
Good question, David. Novelty here deals with newness. Unexpectedness here deals with something non-obvious or surprising. Perhaps this will become clearer if I take an example. So imagine if we decide to entertain a group of 20 friends. We already know how to make soufflés according to a particular recipe. We'll make soufflé for 20 friends this time. We have never made soufflé for 20 people, so it certainly is novel, something new, something we haven't done earlier. On the other hand, we have known this recipe for ages. Something unexpected would be if we come up with a new recipe for this soufflé which tastes dramatically different, surprisingly different. Not just something new, but something unexpected. So far, we have been talking about the product of creativity, the result of creativity, the outcome of creativity. What about the processes of creativity? We've used the term here, some and other. Both of these terms are important. Let's first look at the term other. In this course, we already talked about several processes of creativity. Analogical reasoning is a fundamental process of creativity. We already explored analogical reasoning in the context of design. We just did that when we were talking about design thinking. One might be able to design a new kind of water pump by composing several water pumps in series if one can analogically transfer a design pattern from the domain of electrical circuits, was our example. Similarly, under analogical reasoning, we were talking about the processes that might be used to come up with a model of the atomic structure by analogy to the model of the solar system, which clearly is a creative process that cuts across large number of dimensions of space and time. Another place where we talked about creative processes was when we were talking about explanation-based learning. It seems creative if the robot can go to the kitchen and use the flower pot as a cup to bring you coffee. Here are three other processes of creativity: emergence, re-representation, and serendipity. A simple example of emergence is that if I draw three lines, 1, 2, 3, then a triangle emerges out of it. The triangleness doesn't belong to any single line. I was not even trying to draw a triangle. I just drew three lines and a triangle emerged out of it. The emergence of the triangle through the drawing of three lines is a kind of creativity. Re-representation occurs when the original representation of the problem is not conducive to problem solving. So we re-represent the problem and then commence problem solving. To see an example of this, let's go back to our atomic structure and solar system problem. Suppose that we have a model of the solar system which uses the word the planets revolve around the sun. We also have a model of the atom, and this uses the term the electron rotates around the nucleus. So the model of the sun has the word revolves, and the model of this atom has the word rotates. The two vocabularies are different. If we were to stay with these propositional representations, mapping between rotate and revolve will become very hard. On the other hand, suppose we were to re-represent this problem. We re-represent the atomic structure by drawing the nucleus in the middle and the electron around it. We represent the solar system by drawing the sun in the middle and the earth around it. Then, in this new representation, we can see the similarity, we can do the mapping. This re-representation is another fundamental process of creativity. Serendipity can be of many types and can occur in many different situations. One kind of serendipity occurs when I'm trying to address a problem but I'm unable to address it. So I suspend the goal and I start doing something different. Later, at some other time, I come across a solution and I connect it with the previous suspended goal. The story has it that in 1941 in France, Georges de Mistral's wife asked him to help her open a dress by pulling on a zipper because it was stuck. Mistral struggled with the zipper but couldn't pull it down. Later on one day, Mistral was walking his dog when he found that some birds were stuck to the dog's legs. Curious about this, Mistral looked at the birds closely under a microscope. He then connected the solution, the bird solution, to the opening of the zipper problem. And out of that was born the notion of Velcro, which you and I now use on a common basis. Now, just like the word other was important here, these are three processes. In addition to the processes we already discussed in this class, the word some is also important here. This is not an exhaustive list. There are in fact additional things we can add. For example, another potential process here is called conceptual combination. Let us do an exercise together. Here are a number of tasks that we have come across in this class. For each of these tasks, mark the box if you think that the agent that performed that task well is a creative agent. What do you think, David?
So actually, I marked none of them. It seems to me that for all of these tasks, if an artificial agent that we design accomplishes the task, we're able to go back and look at its reasoning, look at its processing, and figure out exactly how it did it. So it's never going to be unexpected. It's always the output of a predictable algorithm.
Interesting thought, David. Not sure I agree with it. Let's discuss it further. Do you agree with David's assessment that none of these AI agents is creative because we can trace through the process that the agents used? Well, let's look at each of these choices one at a time. The first one says yes, because in order for a result to be creative, it must be novel, and output of an algorithm cannot be novel. Well, there are a few problems with this particular answer. While an output of an algorithm for a small closed-world problem cannot be novel, the output of combinations of algorithms for open-ended problem can, and indeed sometimes is, novel. There are algorithms, for example, that do design or they do scientific discovery whose results are novel. Let's look at the second answer. Yes, because given a set of input, the output will always be the same. Therefore, the product can never be unexpected. The output will depend not just on the input, and not only on the methods of the system, but also the situation in which the methods are situated. The output depends not just on the input and the method the AI agent uses, but also the context in which the AI agent is situated. For example, given the same input but different context for the input, the agent may come up with very different outputs, very different understandings of that same input, as we saw in this section on understanding. The third answer, no, because it defines creativity in terms of the output than the process. This answer too has problems, because sometimes creativity can be defined simply in terms of the output without knowing anything about the process. We can think of a black box that creates very interesting creative music. We may not know anything about the process it is using, but if the output is interesting and creative music, we would consider it to be creative. Personally, my sympathies lie with the fourth answer. But of course, you are welcome to disagree with me. Why don't we continue this discussion on the forum?
Finally, the last topic we'll cover in this class is AI ethics. Often, scientists go about doing science without asking questions about the ethics of the science they do. We are also engrossed in questions of funding and proposals and papers. However, part of our job as scientists is to ask the question about, are we doing the right kind of things? There are a large number of questions connected with the ethics of AI. We'll post a small number here today. There are no easy answers to these questions, so we invite you to discuss these questions on the forum. First, AI ethics pertain to our economy and our society. We have talked a lot in this course about designing AI agents that can act and think and behave like humans. However, in the process, we quite likely will replace some human jobs with robots. We have talked, for example, of robots that can assemble a camera. Does this mean that humans who assemble the cameras today will lose their jobs? Of course, a counter-argument is that new jobs might be created, for example, jobs for designing robots. Nevertheless, there are hard issues about the ethical implications of AI in terms of human economy and society. Second, much of the modern development of AI is driven by defense applications all across the world. We already have drones, for example. It is not far-fetched to imagine a future where there are robot soldiers on the battlefield. What are the implications of introducing robot soldiers? Should we build morality into these soldiers? How do we do so? And if we are to build morality into robots, what does it teach us about our own morality? A third and related question is that if we start building human characteristics like creativity and morality into AI agents, at what point do these agents become like humans? At what point do we start talking about civil rights for these machines because they are indistinguishable from humans? The idea has been touched upon in the popular culture a lot, but it is coming closer and closer to reality. What are the criteria under which we would consider machines to be equal to humans?
So today we've covered some of the most advanced and cutting-edge topics in knowledge-based AI. If anything we've talked about today has really caught your eye, we invite you to check out the course materials where we've provided several readings about each topic. As we said at the beginning, many of the things we've talked about today are open issues that the community is wrestling with right now, so we encourage you to take up the discussion over on the forums. We'll be there participating as well.
Today we'll wrap up this course. It's been a fun journey, but like all journeys, this one too must come to an end. The goal for today's lesson is to tie together some of the big themes we have been discussing and to point to some of the other big ideas out there in the community. We'll start by revisiting the high-level structure of the course. Then we'll go through some of the recurrent patterns and principles we have encountered throughout the course. Finally, we'll talk about some of the broader impacts and applications of knowledge-based AI.
Let us revisit the architecture for a cognitive system. We have come across this several times earlier in this course. We can think in terms of three different spaces: a metacognitive space, a deliberative space, and a reactive space. The reactive space directly maps percepts from the environment into actions on the environment. The deliberative space maps the percepts into actions, but the mapping is mediated by reasoning and learning and memory. So while this is a see-act cycle, this is a see-think-act cycle. The metacognitive space monitors the deliberative reasoning, it sees the deliberative reasoning, and acts on the deliberative reasoning. As we had discussed earlier, it is better to think of these in terms of overlapping spaces rather than disjoint layers. When we were discussing metacognition, we also saw that we could draw an arrow back from here like this because metacognition could also act on itself. This cognitive system is situated in the world. It is getting many different kinds of input from the world: percepts, signals, goals, communication with other agents. Depending on the input and depending upon the resources available to the agent to address that input, the agent may simply react to the input and give an output in the form of an action to a percept, for example. Or the agent may reason about the input and then decide on an action after consulting memory and perhaps invoking learning and reasoning. In some cases, the input that the agent receives might be as a result of the output it had given to a prior input. For example, it may have received a goal, then come up with a plan, but then it receives the input that the plan failed upon execution. In that case, deliberation can give an alternative plan. A metacognition may wonder about why did the planner fail in the first place and repair the planner, not just the plan. Just like reaction and deliberation are situated in the world outside, metacognition in a way is situated in the world inside. It is acting on a mental world. While deliberation and reaction act on the objects in the external environment, for metacognition it is the thoughts and the learning and the reasoning that are objects internally in the mental world. Of course, this input is coming constantly. Even now, as you and I are communicating, both you and I are receiving input. And we're giving output as well. In fact, the cognitive system is constantly situated in the world. It is never separate from the world. There is no way to separate it. There is input coming constantly. There is output going out constantly. The world is constantly changing, and the cognitive system is constantly receiving information about the world. It uses its knowledge and its knowledge structures to make sense of the data about the world. And it decides on actions to take on the world. Recall that we had said that intelligence is a function that maps the perceptual history into action. And to some degree, intelligence is about action selection, about selecting the right output to act on the world. Depending on the nature of the input, the output may vary. If the input is a goal, the output might be a plan or an action. If the input is a piece of knowledge, the output might be internal to the cognitive system. The cognitive system may assimilate that knowledge in its internal structures. If the input is a percept, the output might be an action based on that percept. If the input is new information, the cognitive system may learn from the new information and then store the result of the learning in its memory. The world here consists not just of the physical world, but of the social world as well. Thus, this cognitive system is situated not just in the physical world, but is also situated in the social world consisting of other cognitive systems and constantly interacts with them. Once again, the interactions between these cognitive systems can be of many different kinds: percepts, goals, actions, plans, information, data. Any cognitive system is not just monitoring and observing the physical world, it is also monitoring and observing the social world, the actions of other cognitive systems in the world, for example. Any cognitive system learns not just from its own actions, but also from the actions of other cognitive systems around it. Thus, a cognitive system needs to make sense not just of the physical world, but also about the social world. We saw some of this when we were talking about scripts. There we saw how a cognitive system used a script to make sense of the actions of other cognitive systems. This architecture is not merely an architecture for building AI agents. It is also an architecture for reflecting on human cognition. Does this architecture explain large portions of human behavior? We have covered a fairly large number of topics in this course. You may recall this particular chart from the first lesson. Let us go through each one of these circles one by one and see the connections between them. So under fundamentals, we covered knowledge representations like semantic networks. In fact, we used semantic networks to address 2-by-1 matrix problems. Then we covered a series of problem-solving methods. These were very domain-independent general-purpose methods that did not use a lot of knowledge, but were very powerful. Generate and test, mean-sense analysis, and problem reduction. Then we turned to production systems that had a specific kind of cognitive architecture. Production systems combine reasoning, learning, and memory. Production systems are both a technology for developing AI agents and a theory of human cognition.
Later we talked about planning. And in order to talk about planning, we first proposed a formal language for discussing plans called formal logic. We learned about the different rules and syntax used for writing formal logical statements, and learned why this is very important, that it allows agents to prove the accuracy of their conclusions based on a set of axioms. That gave us a language that we could then use to talk about planning. And as we found out, actually, the origins of planning were in agents making proofs of why a certain set of actions would lead to a certain goal. Here we talked about both partial order planning and hierarchical planning, which are two planning methods that allow agents to make advanced plans for complex tasks, and also allow us to reflect on the way we ourselves plan our actions in a complex environment.
Under common sense reasoning, we covered several important lessons: frames, understanding, common sense reasoning, and scripts. Frames is a structured knowledge representation language that allows us to do understanding. Understanding is such a common everyday activity. We are trying to make sense of the world, but the world is ambiguous. The word take, for example, can have so many different meanings. We saw how frames allow us to disambiguate different meanings of the word take. Under common sense reasoning, we made everyday intuitive inferences about the world around us. While understanding and common sense reasoning were concerned with sentence-level understanding, scripts is more concerned about discourse-level understanding. Script is an even larger yet structured knowledge representation than frames. It too allows us to make sense of the world around us, both the physical world and the social world. Frames also came up in some of the other lessons. In particular, they came up in the lesson on production systems, when we were trying to represent episodic knowledge. They also came up in the lesson on configuration, when we were trying to represent plans and the variables of various plans that can take values.
We talked about learning in many lessons throughout this course, but certain lessons were explicitly and solely concerned with learning. We started off by talking about learning by recording cases, where an agent could build up a case library of its own prior experiences to use for future reasoning. That formed the foundation of analogical reasoning as well, that we'll talk about in a second. We also talked about incremental concept learning and version spaces, two different learning methods for learning about information that's coming in incrementally or bit by bit. That was one of our foundational principles of this class that we discussed at the beginning, and that we'll revisit in a few minutes. We also talked about classification under learning, which is one of the most ubiquitous problems in AI. We talked about how classification involves grouping large combinations of percepts into equivalence classes to allow for easier action selection. Learning also came up in several other lessons that we did throughout this class, including production systems, case-based reasoning, explanation-based learning, analogical reasoning, and learning by correcting mistakes. Meta-reasoning was also deeply connected to learning, where we could learn from our own experiences by analyzing our own prior thought processes.
As David just said, analogical reasoning is another major topic connected with learning. We talked about learning by recording cases, where we are simply assimilating cases by recording them in a growing case library. As a new problem comes, we use methods like nearest neighbor to retrieve the closest case and invoke that case for the new problem. We talked about case-based reasoning, in which we not only retrieve the case, but we also tweak it or modify it in small ways in order to achieve a new goal. In explanation-based learning, we saw how we could connect instances to concept definitions. We constructed explanations that told us how an instance is an example of a given concept. This involved both abstraction and transfer. We also connected explanation-based learning to creativity. Analogical reasoning made the role of abstraction and transfer even more explicit. We talked about cross-domain analogical transfer, for example, from the solar system to the atomic structure. We saw that one needed rich mental models in order to be able to do analogical transfer. We concluded the lesson on analogical reasoning by connecting it with analogical design or design by analogy. Analogical reasoning, too, is closely connected to creativity.
Our discussion of visuospatial reasoning started with our unit on constraint propagation. Constraint propagation was a very abstract and general way of propagating constraints to make sense of a new situation, and it comes up uniquely in visual reasoning, where we use line labeling to make sense of 3D scenes even if they're presented in 2D, where we use line labeling to make sense of three-dimensional scenes even if they're presented in only 2 dimensions. We also saw how constraint propagation could be used for natural language understanding, and we referenced how we might also use it to understand music or tactile information. Then in visuospatial reasoning, we expanded on these notions to discuss whether it would be possible to reason about the world without extracting propositions. This involved looking at scenes in the world where there was no explicit causality, like a glass that's been spilled on the table. We can infer what happened, but there's nothing in the visual scene that tells us exactly how it arose. Similarly, we also discussed how this could apply to other modalities, like tactile information or musical information.
In the unit of design and creativity, we considered lessons on configuration, diagnosis, design, and creativity. You may recall that in configuration, we were worried about very routine, everyday kind of designs. And we did that kind of design by having a library of plans at different levels of abstraction. We selected a plan at a high level of abstraction, assigned values to some of the variables, and then refined the plan at the next lower level of abstraction. All the components were known. We had to decide on the arrangement of the components in configuration. In diagnosis, we were given data about a malfunctioning system, and we had to identify the fault responsible for that malfunctioning. We took 2 views of diagnosis, classification and abduction. In the classification view, this data was mapped into equivalence classes that acted like hypotheses for this data. In abduction, we composed this elementary hypothesis into a composite hypothesis that could best explain the entire data. Design thinking referred to thinking about problems that are ill-defined and open-ended and under-constrained. In design thinking, the problem and solution often co-evolve. The problem doesn't remain fixed, the solution evolves, but that in turn it leads to improved understanding of the problem. Both our understanding of the problem and the solution evolve together. We characterize creativity in terms of the novelty, value, and the non-obviousness of the results. We discussed the criteria under which we would consider an agent to be creative. And we saw how many of the techniques that we have learned in this particular class can compose the fundamental processes of creativity, like analogical reasoning, like visuospatial reasoning, like meta-reasoning.
Then we closed the class by talking about metacognition. Metacognition enabled agents to reason about their own reasoning, or think about their own thinking, or have knowledge of their own knowledge base. We started off by talking about learning by correcting mistakes, where an agent could look at a mistake it's made in the past, isolate the mistake, explain the mistake, and then fix the mistake so it didn't happen again. This was one narrow instance of the broader idea of meta-reasoning. In meta-reasoning, we talked about how metacognition could bring together many of the different methods that we've talked about throughout this class. Meta-reasoning enabled an agent to look at a new problem and select which of its many strategies would be best for addressing that problem. It also would allow an agent to integrate multiple different methods of reasoning at different levels of abstraction. We also talked about how what meta-reasoning operates is also the way in which meta-reasoning operates. Meta-reasoning can reason about case-based reasoning, or it can reason using case-based reasoning. It could, for example, use production rules to conduct case-based reasoning. In this way, it could integrate many different methods at many different levels of abstraction. Finally, this set up a notion of ethics in artificial intelligence. As we're building AI agents that start to have real human-level intelligence, what are the ethical issues? What should we think about replacing certain human jobs with robots? Or what should we think about developing robots that can interact with us on an everyday basis in the natural world? Under what conditions would we consider these agents to actually be human-like?
This summarizes 30 topics that we covered in this class, which is quite a lot. Of course, there is a lot more to talk about each of these 30 topics than we have covered so far. Therefore, we have provided readings for each of the topics, and you are welcome to pursue the readings for whatever topic that interests you the most. We'll also love to hear about your views about this on the forum. In the beginning of this course, we enumerated 7 major principles of knowledge-based AI agents that we'll cover in CS 7637. Let us wrap up this course by revisiting each of the 7 principles. Here is the first one. Knowledge-based AI agents represent and organize knowledge into knowledge structures to guide and support reasoning. So the basic paradigm here is represent and reason. Represent and reason. If you want to reason about the world, you have to represent knowledge about the world in some way. You not only want to represent this knowledge to support reasoning, you also want to organize this knowledge into knowledge structures to guide, to focus the reasoning. Let us look at a few examples that we covered in this course about this principle. Semantic networks not only allow us to represent knowledge about the world, they also allow us to organize that knowledge in the form of a network. We use semantic networks to address the problem of the guards and prisoners dilemma. The advantage of the semantic networks was that they exposed the constraints of this problem so clearly so that we could in fact reason about it. And notice that the organization helps us focus the reasoning. Because of the organization, there's so many other choices, we don't even have to reason about them. Frames were another knowledge structure that organized knowledge and guided and supported reasoning. Given frames for things like earthquakes, we could reason about sentences like a serious earthquake killed 25 people in a particular country. We also use frames to support common sense reasoning. Here Ashok is moving its body part to a sitting position. Here Ashok is moving himself into a sitting position. Here Andrew sees Ashok. Now Andrew moves to the same place as Ashok, and Andrew then moves the menu to Ashok. This is about a story about visiting a restaurant. Once again, there is knowledge structures here. And these knowledge structures are not only representing knowledge, they're organizing knowledge into a sequence of actions. These knowledge structures help generate expectations. So we know what Ashok expects to happen next in any of these situations. We also know how Ashok can detect surprises. When the non-obvious thing happens, Ashok knows it has violated the expectations of the scripts and can do something about it. This is how the scripts support and guide reasoning. We also saw this principle in action when we were talking about explanation-based learning. In order to show that an instance was an example of a particular concept, cup, we constructed complex explanations. In this case, we were constructing the complex knowledge structure on the fly out of smaller knowledge structures. The smallest knowledge structures came out of precedents or examples we had already known. And then we composed the knowledge of these various knowledge structures into a complex explanation to do our reasoning, to guide and support the reasoning. We have seen this principle in action in several other places in this course. This is one of the fundamental principles: represent, organize, reason.
Our second main principle for CS7637 was that learning in KPAI agents is often incremental. This means information or data or experiences arrive one at a time. This is one of the key differences between knowledge-based AI and other forms of AI like machine learning. In those forms, a large amount of information is often given right at the beginning. Here, our agents learn step by step, incrementally. We first encountered this with learning by recording cases. Our agents learned each individual case one by one. The experiences themselves were the increments in this learning strategy. Case-based reasoning also operated on individual cases, but it organized them into much more complex knowledge structures, like tagging them in an array, or organizing them by a discrimination tree. But the fundamental object of knowledge were still individual cases that arrived one by one. We did a complex exercise where one by one we added these new cases into our discrimination tree. Incremental concept learning was, as the title suggests, incremental. Here we received positive and negative examples, one at a time. Based on the difference between our current concept and our new example, and whether or not the new example was a positive or negative example, we would change our concept. This was always done example by example, incrementally. Version spaces involved a very similar kind of knowledge. Here, experiences came one at a time, and we generalized a specific model and specialized the general model to converge down to an understanding of the concept. Finally, learning by correcting mistakes was also deeply incremental. Here, the individual mistakes arrived incrementally, and based on the individual mistakes, our agent modified its knowledge base to repair the cause of the previous mistake. The takeaway here is that many of our methods in learning, reasoning, and memory all involve dealing with information that comes incrementally, bit by bit, instead of processing a large amount of data all at the same time. One can also see that this connects more closely to human experience, where we're constantly experiencing the world, experience by experience, instead of being given a lifetime of experiences all at once.
The third principle of knowledge-based AI agents in CS7637 is that reasoning is typically top-down as well as bottom-up. Ordinarily, we assume that data is coming from the world and most of the reasoning is bottom-up as we interpret the data. In contrast to knowledge-based AI, low-level processing of the data results in the invocation of knowledge structures from memory. These knowledge structures then generate expectations and the reasoning becomes top-down. Frames were an example of this kind of top-down reasoning. We had the input, Angela ate lasagna with her dad last night at Olive Garden. and the processing of this input led it to the invocation of this particular frame. Once this frame has been pulled out of memory, then this particular frame can generate a lot of expectations. For example, was the object alive when Angela ate it? False. Where is the object now? Inside the subject. What is the subject's mood after she had dinner? She was happy. A similar kind of top-down generation of expectations occurred when we used frames to understand simple sentences about earthquakes. Scripts were another example of this kind of top-down generation of expectations and expectation-based processing. Once we have a script, then the script generates expectations about the next action. It tells us what to look for in the world even before that happens. And when that doesn't happen, we know an expectation has been violated and we are surprised. Constraint propagation is another way of thinking about top-down processing. We have input data in the form of pixels representing this cube. We have to infer that this image in fact is that of a cube. We have knowledge about these constraints of various kinds of junctions that can occur in the world of cubes, and this knowledge then generates expectations of what might be a blade and what might be a fold. This notion of top-down processing, using knowledge structures to generate expectations of the world in order to be able to interpret data, is central to knowledge-based AI. It's also deeply connected with human cognition. Some current theories of human cognition think of brains as predictive machines. We're constantly generating expectations. We're constantly making predictions about the world that guide our reasoning, that guide our actions.
Our fourth principle was that knowledge-based AI agents match methods to tasks. At the beginning of this course, we covered several very powerful problem-solving methods like generate and test and means-ends analysis. But because they were very powerful and very general, they also weren't necessarily the best for solving any one problem. We also covered some more specific problem-solving methods like planning that addressed a narrower set of problems but addressed those problems very, very well. We also covered several tasks in this class like configuration and diagnosis and design. These tasks could all be carried out by a variety of methods. For example, we can imagine doing configuration with generate and test, where we generate every possible configuration of a certain plan and then test to see which one's best. We could also do configuration by problem reduction, where we reduce the problem down to the subparts and solve them individually and then compose them into an overall solution. In this way, knowledge-based AI agents match methods to tasks. In some cases, we do the matching. We decide that generate and test is the best way to address this diagnosis problem. In other cases, we might design AI agents with their own meta-reasoning, such that they themselves can decide which method is best for the task that they're facing right now. Note that this distinction between methods and tasks is not always necessarily absolute. Methods can spawn different subtasks. So for example, if we're doing design by case-based reasoning, that spawns new problems to address. And we might address those new problems, those new tasks, with analogical reasoning or with problem reduction. This gets back to our meta-reasoning notion of strategy integration. In this way, knowledge-based AI agents match methods to tasks not only at the top level, but also at every level of the task-subtask hierarchy.
The fifth principle of knowledge-based AI, as we have discussed it in CS 7637, is that AI agents use heuristics to find solutions that are good enough, though not necessarily optimal. Some schools of AI put a lot of emphasis on finding the optimal solution to every problem. In knowledge-based AI, we consider agents that find solutions that are good enough. Herbert Simon called this satisficing. The reason for finding solutions that are only good enough is because of a trade-off between computational efficiency on one hand and optimality of solutions on the other. We can find optimal solutions, but that comes at the cost of computational efficiency. Recall one of the conundrums of AI. AI agents have only limited resources, bounded rationality, limited processing power, limited memory size. Yet, most interesting AI problems are computationally intractable. How can we get AI agents to solve intractable problems with limited rationality and yet give near real-time performance? We can get AI agents to do that if we focus on finding solutions that are good enough, though not necessarily optimal. Most of the time, you and I as human agents do not find optimal solutions. The plan you may have to make dinner for yourself tonight is not necessarily optimal. It's just good enough. The plan that you have to go from your house to your office is not necessarily optimal. It's just good enough. The plan that you have to walk from your car to your office is not necessarily optimal. It's just good enough. Further, AI agents use heuristics to find solutions that are good enough. They do not do an exhaustive search, even though exhaustive search might yield more optimal solutions, because exhaustive search is computationally costly. We came across this notion of heuristic search several times in this course. One place where we discussed this in some detail was in incremental concept learning. given a current concept definition, and a negative example, we arrived at a new concept definition by using heuristics like the required link heuristic. The required link heuristic adds the must clause to the support link between these two bricks. Mean sense analysis was a heuristic method. It said that, given the current position and the goal position, find the differences and then select an operator that will reduce the difference. Because mean sense analysis was a heuristic method, sometimes it ran into problems and did not provide guarantees of optimality. But when it worked, it was very efficient. Another place where we explicitly made use of heuristics was in the generate and test method. Here we had a heuristic which said, do not generate a state that duplicates a previously generated state, which made the method more efficient. Thus, the focus of knowledge-based AI agents is on near real-time performance and addressing computationally intractable problems with bounded resources, and yet being able to solve a very large class of problems in robust intelligence and flexible intelligence. And that happens not by finding optimal solutions to a narrow class of problems, but by using heuristics to find solutions that are good enough to very large classes of problems. This principle comes very much from theories of human cognition. As I mentioned earlier, humans do not normally find optimal solutions for every problem they face. However, we do manage to find solutions that are good enough, and we do so in near real time, and that's where the power lies.
Our sixth principle was that knowledge-based AI agents make use of recurring patterns in the problems that they solve. These agents are likely to see similar problems over and over again, and make use of the underlying patterns behind these similar problems to solve them more easily. We talked about this first with learning by recording cases. Here we assumed that we had a library of cases and that the solution to a former case would be the exact solution to a new problem. Ashok's example of tying shoelaces was similar to this. When we tie our shoelaces, we aren't resolving the problem of tying our shoelaces from scratch. Instead, we're just taking the solution from an earlier time when we tied our shoelaces and doing it again. We assume that the solution to the old problem will solve this new similar problem. In case-based reasoning, however, we talked about how the exact solution to an old problem won't always solve new problems. Instead, sometimes we have to adapt an old problem. Here we assumed that there were recurring patterns in the world that would help us solve these new and novel problems based on previous experiences. Even though the new experience is novel, the pattern is similar to a prior experience. Analogical reasoning is very deeply rooted in this principle. Here we explicitly talked about the idea of taking patterns from one problem, abstracting them, and transferring them to a problem in a different domain. Whereas in case-based reasoning, the pattern was within a domain, here the pattern can span different domains. In configuration, we assumed that the underlying design, the underlying plan for a certain device or product, was pretty similar each time, but there were certain variables that had to be defined for an individual instance of that object. In the chair example, the overall design of a chair is a recurring problem. They all have legs, they all have seats, they all have backs, but the individual details of a specific chair might differ. Now, it might be tempting to think that this is actually at odds with the previous principle, that knowledge-based AI agents can solve novel problems. Here we're saying that knowledge-based AI agents solve recurring problems based on recurring patterns. But in fact, these are not mutually exclusive. Knowledge-based AI agents leverage recurring patterns in the world, but they do so in conjunction with other reasoning methods to allow them to also address novel problems.
So the seventh and last principle of knowledge-based AI agents in CS 7637 is that the architecture of knowledge-based AI agents enables reasoning, learning, and memory to support and constrain each other. Instead of building a theory of reasoning or problem-solving by itself, or a theory of learning by itself, or a theory of memory by itself, we have tried to build unified theories, theories where reasoning, learning, and memory coexist. Memory stores and organizes knowledge. Learning acquires knowledge. Reasoning uses knowledge. Knowledge is the glue between these three. One place where we saw reasoning, learning, and memory coming together very well was in production systems. When reasoning failed and an impasse was reached, then memory provided some episodic knowledge, and the learning mechanism of chunking extracted a rule from that episodic knowledge, and that rule broke the impasse and reasoning could proceed apace. This was a clear example where reasoning, learning, and memory came together in a unified architecture. In logic, memory, or the knowledge base, may begin with a set of axioms, and those set of axioms decide what we can prove using that particular logic. To look at the problem conversely, depending upon the reasoning, we need to put things in the knowledge base so that the reasoning can be supported. Explanation-based learning was another place where reasoning, learning, and memory came together so well. Memory supplied us with the earlier precedents. Reasoning led to the composition of this explanation, which explained why an instance was an example of a cup. This led to learning about the connections between these various precedents into an explanation. Learning by correcting mistakes was yet another example of learning, reasoning, and memory coming together. When a failure occurred, then the agent used its previous knowledge, memory, to reason and identify the fault responsible for the failure, reasoning, and then corrected that particular fault, learning, in order to get the correct knowledge. Thus, the knowledge-based paradigm says that we want to build theories that are unified, that connect reasoning, learning, and memory. And this also connects very well with human cognition. Human cognition, of course, has reasoning, learning, and memory intertwined together. It is not as if memory and human cognition works by itself, or learning works by itself, or reasoning works by itself. You cannot divorce them from each other. Knowledge-based AI is a dynamic field with a very active research program. There are a number of exciting projects going on right now. Here is a small list of them. Callow is a project in which a cognitive assistant learns and organizes knowledge. Callow, in fact, was a precursor for the Siri program of Apple. Psych and OMCS. OMCS stands for Open Mind, Common Sense. Psych and OMCS are two large knowledge bases to support everyday common sense reasoning. Wolfram Alpha is a new kind of search engine that uses some of the same kind of knowledge structures we have considered in this particular class, different from many other search engines. The three projects in the right column are projects here at Georgia Tech. Vita is a computational model of visual thinking and autism. In particular, it solves problems on the Raven progressive matrix test using only visuospatial representations. Dramatis is a computational model of suspense in drama and stories. Recall that in this class we talked about a theory of humor and surprise. Dramatis tries to do the same thing for suspense. Data is a system for supporting design based on analogies to natural systems. We had come across this idea of biologically inspired design earlier in the class, and Dane supports that kind of biologically inspired design. We have provided references to these and many other knowledge-based AI projects in the class notes. You are welcome to explore depending on your interests.
This brings us to the end of the course. There are many more topics that we could talk about, and we encourage you to look at the additional readings for the course. As we said at the beginning, we have had a lot of fun putting this course together, and we have learned a lot too. We hope you have enjoyed the course as well.
We're also really eager to get your feedback. What did you enjoy about this course, and what could have been improved? What surprised you about this course, either in the content or in the way it was administered? Are there things you've seen other courses do that you wish we had done? Or are there things that we did that you'd like to see other courses do?
We are very interested in your answers to these questions, so please feel free to contact either one of us with your answers and fill out the course survey as well.
We'd also like to thank several people for helping make this course possible. First, our video editor, Aaron, who's done a phenomenal job making these videos look so good and frankly making us look presentable. We'd also like to thank the rest of Udacity, especially Jenny Kim, Jason Barros, and Katie Reichelt, for providing a great infrastructure for course development.
We'd also like to thank our colleagues here at Georgia Tech, including David White at the College of Computing, and Mark Weston and the staff of the Georgia Tech Professional Education Department. It's been a real fun journey for us. We expect to hear from you. We hope it's the beginning of a beautiful friendship.